Sir.
Okay, madam. Visible, madam.
Good morning to all the participants, and a warm welcome to esteemed resource person, Professor T. Suman Kumar, School of Mathematics and Science, Statistics, University of Hyderabad. Dear colleagues, my dear students, and my dear participants, before starting the program, I request our principal madam, Dr.D.KALYANI, to deliver her opening remarks. Thank you. Thank you, madam.
Good morning, respected resource person, esteemed participants, and a warm welcome to this one-day national webinar organized by the Department of Mathematics and Department of Computer Science in collaboration with IQAC and JKC. I extend my sincere appreciation to both departments for taking the initiative to organize this insightful webinar on uniformly continuous functions and applications of Python. This webinar holds significant value as it caters to a diverse audience ranging from students to professors, professionals, researchers, and enthusiasts. By shedding light on the importance and practical applications of uniformly continuous functions, participants stand to gain valuable insights applicable across various fields and levels of expertise. Python, being a versatile programming language, offers robust libraries such as NumPy and SciPy, which are indispensable for mathematical computations. These libraries empower users to tackle complex mathematical problems, perform numerical analysis, and implement algorithms with efficiency and ease. With its intuitive syntax and extensive documentation, Python emerges as the preferred choice for mathematical solutions and research endeavors. I am optimistic that this webinar will serve as a fruitful platform for knowledge exchange and will significantly contribute to enhancing the participants' understanding of subject matter. My heartfelt congratulations to the faculty for spearheading this program and extend my best wishes for its success. Let us embark on this learning journey together with the aim of expanding our knowledge and skill set. Thank you. Thank you.
Now, introduction of our resource person, Professor T. Suman Kumar, by our IQAC coordinator, P. Kusum Kumari.
Good morning, all the participants. Thank you for giving me the privilege to read out the profile of Dr. T. Suman Kumar. Dr. T. Suman Kumar is a distinguished professor at the University of Hyderabad, India, where he has held various academic positions over the years. With a rich academic background, Dr. Kumar completed his doctoral studies at University Sorbonne, Paris, under the esteemed guidance of Professor Benoit Parthen. His doctoral research focused on age-structured nonlinear renewal equations, contributing significantly to the field of mathematical biology. Prior to his PhD, Dr. Kumar obtained his Master of Science degree in Applied Mathematics from the University of Hyderabad, India, where he excelled academically, laying a robust foundation for his future academic endeavors. Dr. Kumar's research interests encompass a wide array of topics, including population dynamics, mathematical biology, and numerical analysis of partial differential equations. With over 20 publications in esteemed journals such as International Journal of Computer Mathematics, Computational and Applied Mathematics, and Numerical Algorithms, Dr. Kumar has made substantial contributions to the field, offering valuable insights into complex biological systems and mathematical modeling techniques. In addition to his research endeavors, Dr. Kumar is an accomplished author, having opened a book, a first course in ordinary differential equations, and contributed to other related works. This comprehensive textbook serves as an invaluable resource for students and educators alike, providing a thorough understanding of differential equations and their applications. Furthermore, Dr. Kumar has actively supervised several PhD and master's projects, demonstrating his commitment to fostering the academic growth and development of aspiring mathematicians. Dr. Kumar's academic achievements have been duly recognized through prestigious awards, including the Young Scientist Award in Mathematical and Physical Science 2017 from the Telangana Academy of Sciences. His expertise extends beyond academia, as he frequently delivers invited talks and seminars at institutions and conferences worldwide. Dr. Kumar is also actively involved in organizing workshops on topics such as complex analysis, differential equations in population dynamics, and heat transfer modeling, where he serves as a resource person, sharing his knowledge and expertise with fellow researchers and students. Moreover, Dr. Kumar has made significant contributions to the academic and administrative aspects of the University of Hyderabad. He has served on various committees, including the School of Board of Mathematics and Statistics, the Library Committee, and the Admission Committee, among others. His leadership and dedications have been instrumental in shaping the academic landscape of the university and fostering a culture of excellence and innovation. In summary, Dr. T.S. Kumar stands as a beacon of academic excellence in the field of mathematics and mathematical biology. His multifaceted contributions across research, teaching, mentoring, and administrative responsibilities, all of which reflect his unwavering commitment to advancing knowledge and nurturing the next generation of mathematicians and researchers. We are happy to have you here, sir, as our resource person. Now I hand over the program to the coordinator.
Thank you, madam. Now I am handing over this session to our resource person, Professor T. Suman Kumar. Thank you, sir. You can proceed, sir.
Very good morning to everybody who is present there. First of all, I would like to thank Dr. KGR and the principal of her school, her college, for giving me this opportunity to interact with youngsters. I always wanted to have interaction with young minds. Okay, fine. So today we are. I'll come back to this thing very quickly. Okay. Today we want to have discussion on uniformly continuous functions. Okay. If you find anything not very much accessible due to whatever reason, you please let me know. You just stop me and I'll try to interact with you or try to put the things in a slightly different way so that you can understand. Okay. So please feel free to stop me anywhere. Okay. All right. So is there a way that if students have questions can be stopped? Is there any mechanism for teachers, or how do I know that students have questions? Madam, am I audible? Hello. Hello.
Sir, audible, sir.
You're right. Okay. So what is the mechanism? What is the mechanism available so that I understand students have some questions in the middle of the lecture? Are there some teachers who can is there anybody who can ask questions?
Right hands.
Sir, there is a digital board, sir, display, sir. We are along with our students, sir.
Okay, fine. Fine. The thing is, when I share my screen completely, I may not be able to notice if somebody raises hand. So what you do is you please ask orally. Okay, instead of raising hand, you can one of the teachers can orally ask me to stop, and then I'll minimize that thing, and you can and then I can talk to student. Okay, straight away.
sir. Okay, sir.
Okay, fine. Thank you. So that's important instead of just one way delivering lecture. All right. So fine. Now let me start sharing my screen. Okay. Is the screen visible? Is it visible?
Yes, sir. Yes, sir.
Okay, fine. All right. So let me start with right. Uniform continuity. So first of all, let us start with what is a continuous function. Okay, and let me restrict myself with my entire lecture to R or subsets of R. In particular, let me restrict myself to subsets which are intervals. Okay, a typical notation for interval is J. Okay, so J is of the form either closed interval AB or it could be sometimes open interval AB or some interval. Okay, it could be semi-open, semi-closed. Okay, like that. This is my typical interval. Maybe it could be like this. Okay, and then what are these A and B? A comma B. Okay. So here A and B are any numbers, including infinity. Okay. By the way, infinity is not a real number, but I hope you understand what do I mean by when I say closed zero, open infinity, or open zero, open infinity. Okay. In that sense, I'm saying. Okay. Fine. So let me first recall what is a continuous function. Okay. Suppose you take a function f from J to R. Okay, and then you take x naught is a number in J. When do you say a function is continuous at x naught? So, okay, so we say that it's continuous at x naught if, let us draw the picture and see what we mean by continuity at x naught. Suppose this is a function f and you have x naught here. What do we mean by continuity at x naught? So this point, if this is x naught, this point is x naught comma f of x naught. All right. What do you mean by continuity? Continuity means, okay, so suppose you take, what about this guy? This is f of x naught. Okay. Now for whatever epsilon you choose, okay, and you consider an interval around f of x naught. Interval around f of x naught means how does it look like? Interval around f of x naught. So f of x naught minus epsilon, f of x naught plus epsilon. Okay. So this is the interval around f of x naught. Okay. For every epsilon, you take an interval around f of x naught, then there exists a small interval around x naught. That means there exists delta such positive such that you take a small interval around x naught, that means small interval around x naught means what? X naught minus delta to x naught plus delta. Then you look at the image of this interval. What do you mean by image of this interval? If x acts on it, okay. So what is the image of this interval? Is this image of this interval? So how does it look like? This thing, right? So all the terms which are here, this is nothing but image of this interval. So whatever is in this, let me put it in a different color. Oh, wait, let me use this. Yeah, use different thickness. Okay. So this portion that is in red color is the image of this interval x naught minus delta to x naught plus delta. Okay. You see this image of, you take any point here in this interval and you look at f acting on that point, that is somewhere here. That means it is in this red portion. Okay. And you observe that this red portion is completely inside this interval, f of x naught minus epsilon to f of x naught plus epsilon. So this is f of x naught minus epsilon to f of x naught plus epsilon. Okay. So if such a thing happens, then you can say that f is a continuous function. Of course, in your textbook, you would have written this definition in a slightly different way. So let us see how you would have written it. You would have written that, okay, if what is the meaning of f of x naught? What is the meaning of something is a subset? This is a set, okay? This is a set. This set is a subset of it. What does it mean? That means you take any point in this set, it is a member of this set, right? So any point in this set looks like what? F of this interval, right? X naught minus delta to x naught plus delta. A typical point in this set is of the form, okay, f of x. A typical point in this set looks like f of x, where x belongs to x naught minus delta to x naught plus delta. Okay. This f of x is a typical point in this set. So what should f of x, where does this f of x lie? F of x is a typical point here. It lies in this interval. Okay. So f of x belongs to this interval. Which interval? F of x naught minus epsilon to f of x naught plus epsilon. Okay. This is f of x naught. This length is epsilon. So what happens? This is f of x naught minus epsilon. And this is f of x naught plus epsilon. All right. Now f of x belongs to this interval means what? F of x could be here or it could be here. But no matter where is f of x, the distance between f of x and f of x naught, you see, this distance between f of x and f of x naught is less than epsilon. In other words, modulus of f of x minus f of x naught is less than epsilon. Okay? Whatever I have written here, I'm rewriting in this way. Right? Whenever this f of a typical member in this set is what? F of x. So that means whenever x belongs to x naught minus delta to x naught plus delta. Yeah. Right? In other words, again, if I use the same argument, I have x naught here, x naught minus delta is here, x naught plus delta is here. If x belongs to this interval, means x could be here or here, no matter where it is, whether it is on the left of x naught or the right of x naught. Yeah. Okay. So no matter where is this x, whether it is on the left or right, what I can say is x minus x naught is less than delta. Okay. So when I said f of this interval is a subset of an interval around x naught, an interval around f of x naught. This is equivalent to saying that modulus of f of x minus f of x naught is less than whenever x belongs to this interval. And this is equivalent to saying that f of x minus f of x naught is less than epsilon whenever x minus x naught less than delta. Okay. So therefore, here we have actually shown that our definition is nothing but for every epsilon greater than 0, there exists delta positive such that, of course, now most important thing is I am having this discussion for continuity at x naught because I'm fixing x naught here. Okay. So let me write the definition. Say that f from j to r is continuous at x naught belongs to j if for every epsilon positive there exists delta positive such that f of x minus f of x naught is less than epsilon whenever x minus x naught is less than delta. All right. Yeah. Here, I would like to emphasize two things. First one, okay, so this is better. Yeah, the first one is this delta depends on x naught as well as epsilon. Okay. Okay. Now I'll write another trivial one. We say that f from j to r is continuous if f is continuous at every point x naught belongs to j. Okay. If a function is continuous at every point in the interval, then we simply say that a function is continuous. Okay. So we don't really mention about any point. If we say that we are not mentioning the point at which I am discussing continuity, it actually means that this is the same as function is continuous throughout. Okay. Right. All right. Now, what is the meaning of this thing? That means whatever x naught you choose, okay, whatever epsilon, whatever x naught you choose, at that x naught f is continuous, right? In other words, for every x naught, okay, it is automatically going to x naught. Okay. So whatever x naught I am considering, f is continuous at x naught. Okay. In other words, whatever x naught I choose, what do you mean by f is continuous at x naught? Whatever epsilon I choose, there exists delta positive such that x minus x naught is less than delta implies f of x minus f of x naught less than epsilon. Okay. Yeah, this is another way of saying that f of x minus f of x naught is less than epsilon whenever x minus x naught is less than epsilon. So these two are equivalent. Okay, it's the same thing. I'm writing in a different language. That's it. This whenever, when I use the phrase whenever, when I use this word whenever, this is actually the same as this. Okay, these two things are same. Okay, whatever I'm putting in these two boxes, these two are same. If you want to use English word, then use whenever. If you purely want to write everything in terms of mathematics, use this notation. Okay, now you have to understand the importance of order of quantifiers. Right. So this is what I keep emphasizing. I keep telling the students that if you have two different quantifiers for every and there exists. Okay. There exists and for every. Okay. Suppose you take for every P, there exists Q. And there exists P. Oh, sorry. What is it? Maybe I write there exists Q for every P. So what's the difference? Are these two things same or different? Can I interchange the order of the quantifiers? This is an important question. Can I interchange the order of the quantifier? You can think whether you can do it or not. So are these two things same? Can I interchange? Or if I interchange, what happens? What goes wrong? Or okay. So the most important feature is these two things are different. I am not allowed to interchange these two things. Okay. Not interchangeable. Okay. I'll tell you why you should not interchange. It is because when you say for every P there exists Q, that means if you fix P, then according to P, or maybe depending upon P, your Q value exists. There exists Q depending upon P. If you change this P, consequently Q also might change. Okay. If P is 0.1, Q could be 10. If P is 0.01, Q could be 100. You know, if you change P, Q is also changing. Okay. So in other words, I can have this thing. For every P, there exists Q such that PQ is equal to 1. What does it mean? It means if I fix P, okay, if I fix P positive, then there exists Q such that PQ is equal to 1. But can I say this? There exists Q positive such that for every P positive, PQ equal to 1. Answer is no. Because here, what does it mean when I write there exists first? When I say there exists first, it means that this Q is independent of P. No matter what P you choose, okay, no matter what P you choose, P into Q equal to 1. Is there any such Q such that PQ equal to 1? No matter what P you choose, there is no fixed Q. Okay, so that means here when I put there exists first, that means I'm fixing Q independent of okay. This is an important thing. Fix Q independent of P. Here, when I write for every first and there exists later, that means here it actually means that Q depends on P. Here it means Q is independent of P. Okay. So this is the main difference between order of the quantifiers. Right. Now, okay, with this small discussion on order of quantifiers, what we do is we'll just see what we have written. Okay, so I can insert space. Okay. Yeah. we have written that for every x naught, for every epsilon, there exists delta. That means from our discussion, this delta depends on both x naught as well as epsilon. If I change x naught, this delta changes. Or if I change epsilon, this delta changes. Okay. So the moral of the story here, what from the discussion what we have so far, this delta depends on x naught and epsilon. Okay. Right. Of course, you can just look at some examples. You can just look at some examples. For instance, you take f of x equal to x square. Okay. Take this function and then take take x naught is equal to n. Okay, maybe instead of x naught equal to n, maybe you just take control. Okay, right. Yes, somebody wants to ask something. Somebody raised hand. Okay. Okay. So you take f of you take x naught is equal to, let's say, 10. Okay, and epsilon is equal to let's say 0.1. Now I want to find delta. So what does it? How does it work? So we need to find delta such that what should happen? X naught minus the, if x belongs to, oh no, what is the, if you have to look at in terms of this thing, if x minus x naught less than delta implies f of x naught minus f of x less than epsilon. This is what we want, right? In other words, I want delta such that 10 minus x is less than delta implies, what is f of x naught? 100, right? F of x is x square. F of x naught, it means x naught square. In particular, x naught is this. Okay. F of x naught, f of x is less than 0.1. No, wow, sorry. This is okay. What is f of x here? In this case, x square, right? Let us write x square. Let's write x square. So what we want is, we want to find delta such that this is 10 minus x into 10 plus x less than 0.1. Okay. So this entire thing, I want to find delta such that what should happen? 10 minus x is less than delta implies this quantity into this is less than 0.1. How do you find it? So from this, what do you want? This is equivalent to 10 minus x is less than 0.1 by 10 plus x. Okay. What is that I want? I want delta such that 10 minus x less than delta implies 10 minus x less than this also. Okay. So I have same quantity. So can you compare delta and something this? Now, what can you say about delta? From this, can you conclude something about delta? Suppose your interval is, let's say, open interval 0 infinity to let's say r. Okay, because I'm simplifying things here. Yeah, observe that this is less than 0.1 by 10, isn't it? X is anyhow positive, so 10 plus x is bigger than 10 and it is in the denominator, so therefore I write this. So what do you have? 10 minus x less than delta implies, for in modulus, 10 minus x less than 0.01. Okay, 10 minus x less than delta implies this. So what can you say about delta? Yeah. So from this, what do you conclude about delta? I conclude that delta is less than 0.01 or less than or equal. Suppose delta is bigger than 0.01, then such a thing cannot happen, right? Okay, so delta is less than 0.01. Okay, this is a possibility. Suppose instead of 10, if you take 100, then what would have happened? This is 100, just replace 10 with 100, that's it. This will be 100, this will be 100 square. Again, I write 100 minus x into 100 plus x. Do exactly the same thing. Okay. Then you end up getting what? If x naught is 10 square, of course, so this is what? 10 power minus 2, right? Then using the same arguments, we obtain this delta has to be less than or equal to 10 power minus 3. Okay. And similarly, if x naught is equal to 10 power maybe 15, then delta is less than or equal to 10 power minus 60. So what is the trend that we observe? If x naught is changing, then delta is also changing. Okay, If x naught becomes larger and larger, then delta is becoming smaller and smaller. Okay, you understand? So this delta is depending heavily on x naught. Of course, it depends obviously on epsilon. Okay, if you change your epsilon to be, let's say, instead of 0.1, if you take 0.01, then what will be this one? Delta will be 10 power minus 3. If you keep epsilon equal to 10 power minus 3, then delta will be 10 power minus 4. If epsilon is 10 power minus 10, delta is 10 power minus 11. Okay, so these kind of calculations actually help you, to see how your delta depends on x naught as well as epsilon. X naught as well as epsilon. Okay, right. So what do you understand from this example? What we understand from this example is, okay, this delta depends on x naught. Okay, right, and it is at least 0.1 by x naught in that way. So can you find one fixed delta positive such that it works for every x naught? So what is the dependence here? Okay, delta is something like 0.1 by 0.1 by, what is it? Maybe x naught plus 1 or something. Okay, so you can't really find out. Okay, maybe I'll put this, I'll remove this. Really, what is it? Okay. Okay. So this, the question is, can you find delta positive such that delta is less than 0.1 by x naught plus 1 for every x naught positive? Is it possible? If x naught becomes larger and larger, then what about the denominator? It is going to infinity. So therefore this fraction, entire fraction, this goes to 0. Okay, and this guy goes to 0, and this is anyhow 0. So by sandwich lemma, what does it, where does this delta go? As x naught becomes larger and larger, this delta is going to 0. Okay, so answer for this question is no. We can't find. That means in another way of asking the same question is that can we find a uniform delta positive which works okay. So rephrasing this question is okay. 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 So rephrasing this question is, for given epsilon positive, okay, can we find a uniform delta which works for every x naught? Okay. So this is rephrasing the same question. Again, therefore, answer for this question is also no, because I'm asking the same question again and again in different ways. So answer is no. Okay. So this actually leads to the definition of uniform continuous function. Okay. See, we have just come to the statement, or maybe we have just come to the motivation of this uniform continuous function. Okay. Okay. So you take this another example before I finally conclude the examples and give the definition. Example 2, f of x equal to x. Okay. And of course, f is a function from R to R. Here, now epsilon is given to you. Okay. Let x naught is equal to 10, like before. Epsilon equal to 0.1. Now we need to find delta as before. So what is that? What is the delta that we choose? We want delta positive such that x minus 10 x naught less than delta implies f of x minus f of x naught less than epsilon. In other words, we want delta positive such that this is less than delta implies what is f of x? F of x is x, f of x naught is 10. This is 0.1. So what is delta here? Here we can choose. Okay. We can choose delta is equal to 0.1. Okay. Now instead of 10, if you put 100, then what happens? Nothing. It's like x in the place of x naught you have 100, and then here you will have 100. No change. Still I can take delta equal to 0.1. So no matter what is x naught, okay, we can choose delta equal to 0.1 here. Okay, here this, okay, in other words, okay, in other words, delta depends only on epsilon. Delta depends only on epsilon, and it is independent of x naught. Okay, so we have seen two examples where in one example delta depends on x naught, in another example delta does not depend on x naught. Okay. So using the same argument, you can do it. Maybe I'll insert space and then write down here. Yeah, I say that. So using the same argument, we can show that no matter what is x naught, we can choose delta equal to 1. Okay, that's perfect. Okay, so from these two examples, we have understood that there are two types of functions. One type of function looks like this, f of x equal to x square type of function, where delta depends on both epsilon and x naught. And there are some types of functions where delta depends only on only on epsilon, but not on x naught. Okay. So this second type of functions, yeah, somebody wants to raise the question. Oh my God, somebody is raising the hand. Is all right. Fine. So this delta depends only on epsilon, right? Then, yeah, here. Now we are ready to give the definition of. Okay. So I say that. Okay. Oh my God. So there's some sound is coming. Okay. Right. Yeah. So yeah. So we say that a function f from j to r. Okay, these two examples motivate us to give what is a uniformly continuous function. Okay, we say that a function function from j to r is uniformly continuous if the second type of if it has the behavior like the function which is in example 2. That means this delta should not depend on the location of x naught. Okay, so if for given epsilon positive, there exists delta positive such that now I write for every x naught here. Earlier, where did we write x naught? I wrote x naught before this there exists. Okay, if you look at my earlier definition of continuity, x naught came first. You see, x naught came first and then delta came later. Okay, for every x naught was at the beginning, and then this there exists delta came later. That means this delta may or may not depend on x naught. Okay, now what I'm doing? This there exists delta coming first. Okay, coming before this for every epsilon. That means this delta doesn't depend on x naught. Okay, such that for every x naught in j, okay, something should happen. What is that we have? What is that we have? X minus x naught less than delta implies f of x minus f of x naught less than epsilon. All right. So this is the most important difference between continuity and uniform continuity. Okay. Once you understand the definition properly, then proving results, or applying the statements to various, applying the statements of the theorems to various contexts, that comes automatically. Okay. So you should spend more time in understanding and getting motivated to the definition. Okay. But unfortunately, what happens is students are, they are rushed to theorems before spending much time on definition. Okay. Suppose because definitions are not very much important in the examination point of view. That's what you think. But if you don't focus really on definitions, spend more and more time in understanding the definition and then looking at the example and so on, then you don't understand completely what the theorem is saying and how proof goes. That's why most of the times you end up by hearting the proofs. Okay, this is not a good way of learning mathematics. Okay, you should focus more on understanding the definitions, take your time, and then proofs of the theorems come very naturally. Okay, they just they just follow immediately from the definition. Okay, most of the proofs. Okay, right. Now let us see what is the definition that is typically given in textbooks. In textbooks, what people write is, instead of using x naught and x, they say that for every a typical this thing is for every epsilon there exists delta positive such that x minus y less than delta implies f of x minus f of y less than epsilon. Okay, for every x and y in J. Okay, this is a typical exam definition that is given in standard books, and you try to mug up without actually understanding what it is. So that's why you means general students. I'm not particularly pinpointing individuals in the audience, but I'm saying that mostly students tend to by heart this one and then try to prove results or try to by heart results. No, you should not do that. Okay, understand what is the definition, and then things follow immediately. Okay. So, and then from the very after you see the definition, from the motivation, what are the can you quickly give a uniformly continuous function? F of x equal to x. Okay, where f is a function from R to R. Is a uniformly continuous function. Is a uniformly continuous function. Example 2, f of x equal to, f from open interval 0 infinity to R, f of x equal to x square is not a uniformly continuous function. It is not uniformly continuous. Okay, this is what we have started with. Now let us see. There are some obvious remarks from the definition. So uniform continuity is a global property. That means you should say uniformly continuous over an interval. Okay. Whereas continuity, you talk at a point. From the very definition of uniform continuity, what is the uniform continuity definition? This delta should not depend on location of x naught. When I say it does not depend on location of x naught, you should immediately think of what do you mean by independent of location of x naught. First of all, I should know what is the region where x can take values from. Okay. Therefore, you should always ask, when I say f is a uniform continuous function, you should always ask for domain of f. Okay. Uniformly continuous. That's why uniformly continuous on the domain, on an interval. This kind of things we'll see. Uniformly continuous on J. On the other hand, you say continuity at x naught. Okay. This is what you have. Uniform continuity as a whole, you talk always, but continuity at a point. Of course, you can still say continuity in an interval. Okay. Continuity on J and uniform continuity on J, these two are different things. Okay. So typically continuity is a local property. Right. Say that continuity is a local property. Okay, why do you say it's local? Because you talk about continuity at a point. Though you say a function is continuous on an interval, essentially what is it you need to check in order to check if it's continuous at continuous in the entire interval? You need to take each and every point and then check continuity at each and every point. Then only you can conclude that it is continuous throughout. So essentially it boils down to checking continuity at a point. Okay. So this is what I mean by continuity is a local property and uniform continuity is a global property. Okay. Now, how do we okay. Now let us look at some important properties of uniformly continuous functions. Okay, some important properties, and then we'll come back to some more examples if time permits, and a thumb rule to check whether a function is uniformly continuous or not. Okay, I'll give you two very important, maybe three important tools to check whether a function is uniformly continuous or not. Okay, I'll try to give at least three important tools to check whether a function is uniformly continuous or not. Okay, so first let us see some properties of continuous functions. Sorry, some properties of uniformly continuous functions, you know, which are very important. See, as soon as you have seen continuous functions and seen some examples, you would have proved algebra of continuous functions. That means sum of two continuous functions is continuous, you know, and difference of two continuous functions is continuous. Composition of two continuous functions is continuous, you know. Sum of two, difference of two, okay, and then this scalar multiple you would have seen. It's actually I'll do one thing. This is instead of dealing with okay. Why do I write this unnecessarily? Difference. Once I have sum, that is good enough. Scalar multiple of scalar. Okay, sum of two continuous functions is continuous. Scalar multiple of a continuous function is continuous. Composition of two continuous functions is again continuous. Okay, so these are the three results that you have seen when you studied continuity. And these three results are in fact true for uniformly continuous functions also. Okay, uniformly continuous functions is again uniformly continuous. Okay, and you have the same result for scalar multiple, and then composition of two uniformly continuous functions is uniformly continuous. Of course, these things are exercises. I can leave these three results as exercises for you, and you should sincerely try to prove this from the definition of from the definition of uniformly continuous functions. And if you look at the proofs of these results in the context of continuous functions, same proof you try to export, you try to mimic, and then get the result in the context of uniformly continuous functions. Okay, so hint for this exercise is use the proof from the context of from continuous functions case. Okay, use the proof from this plus definition of uniform continuity. These are the only two ingredients that you need, and definition of uniformly continuous function I gave you, and proofs of these three results your teacher would have given in the when the teacher taught you continuous functions. Okay, you can do these exercises, or you can just show it to your teacher, and he or she will correct. Okay, there are some errors. Okay, next thing is some scalar multiple. On the other hand, you would have proved the product of two continuous functions is continuous, right? Product of two continuous functions uniformly continuous. Okay. So you would have proved that product of two continuous functions is continuous. Now, what do you say about product of two uniformly continuous functions? Is it uniformly continuous or not? From the examples that we have. F of x equal to x is uniformly continuous. We have seen that f of x equal to x square is not uniformly continuous. So from this, can you say something? If you restrict f of x equal to x when x belongs to closed 0 open infinity, right? Still the same problem, still f is uniformly continuous, though you restrict your domain to closed interval 0 open infinity. So from this, we can conclude that from the two examples that we have seen, we conclude that product of two uniformly continuous functions, okay, need not be uniformly continuous. Okay? Product of two uniformly continuous functions need not be uniformly continuous. Wonderful. Up to sum if sum of two uniformly continuous functions is uniformly continuous and scalar multiple is there, then from this you can conclude that difference of two uniformly continuous functions is uniformly continuous. Okay, because if you have to deal with f minus g, what I'll do is I'll write it as f plus minus g. Okay, f is uniformly continuous, g is uniformly continuous. Therefore, minus g is uniformly continuous because scalar multiple of uniformly continuous function is uniformly continuous. The minus g is uniformly continuous, f is uniformly continuous. Therefore, their sum is uniformly continuous. Okay, yeah. Now, I'll give you a very important result. It is called sequence criteria. To check uniform continuity. Okay. F is uniformly continuous and J if and only if the following things should happen. Yeah, usually for continuity, there is a sequence criteria, right? F is continuous at x naught. In terms of sequences, how do you say? If xn converges to x naught, then f of xn should converge to f of x naught. Okay? So this is a sequence criteria for continuity. And we want to have same thing for uniform continuity. For uniform continuity, what happens is one sequence is not enough to deal with uniform continuity. You need two sequences. So how does it, what do you mean by two sequences? You see carefully. If xn and yn are two sequences, if for every xn and yn with the property that xn minus yn goes to 0, okay, you take two sequences with the property that xn minus yn goes to 0. For instance, n plus 1 by n. Okay, xn could be n, xn equal to n, and yn is equal to n plus 1 by n. xn, I'm not saying that xn converges. Xn could diverge. See, for instance, xn equal to n, it's a divergent sequence. Yn is this is another divergent sequence. But the difference between xn and yn, what is xn minus yn here? In modulus, that is 1 by n. This is a convergent sequence. Okay, I want such kind of sequences. What is that I want? I want a sequence. I want two sequences with the property that, what is the property that I want for those two sequences? Difference between that sequence, okay, that difference xn minus yn should tend to 0. For every sequence with this property, we have their images also should satisfy the same property. Okay. F of xn minus f of yn should converge to 0. Okay. So this is a very powerful technique. If such a thing happens, then you say that f is uniformly continuous. For instance, I can apply the sequence argument for, I quickly give you an application for the known result. Suppose you take f of x equal to x square on, let's say, open interval 0 infinity. Okay, I choose one xn is n, another yn is equal to maybe n plus 1 by n. Okay, then what is the property that xn minus yn has? Choose this, then xn minus yn converges to 0. No problem. But what about f of xn minus f of yn in modulus? So what is it? N plus 1 by n whole square minus n square. So what is it? So this is 2 n square plus 1 by n square plus 2, right, minus n square. This n square I cancel. So this is something like 2 plus 1 by n square. Obviously this does not go to 0, right? If it is uniformly continuous, then it would have gone to 0. Therefore, you conclude that f is not uniformly continuous function. Okay. Now application 2, you take f from 0 infinity to r, f of x equal to x square. No, sorry, not x square. Something like cos x square. This is slightly complicated, I think, in order to estimate. Of course, still you can do it, but it is very easy to apply this. Okay, I know that cos function takes 1 when x is cos theta is 1 when theta is a multiple of 4 pi. Okay, or maybe 2 pi. Okay, it's a multiple of integral multiple of 2 pi. So therefore, what I do is I take x is equal xn is equal to, I'll write 2n pi square root, such that when you square it, you have 1. Okay, and you take yn is equal to 2n pi plus pi by 2 square root of it. Okay, then what is the difference between xn and yn in modulus? So what is it? 2n pi plus pi by 2 minus 2n pi. All right? Yeah, so what is it? If you rationalize the numerator, then I end up getting pi by 2 into 1 by sum of these two things. Okay, 2n pi and 2n pi plus pi by 2. Okay, anyhow, so as n goes to infinity, what happens? This guy tends to 0. So xn and yn these are two correct sequences that I can work. So what about f of xn minus f of yn? What is f of xn? That is cos xn square and cos yn square. So cos xn square is what? Cos 2n pi, that is 1. And cos yn square is this, that is 0. It's a constant function 1, which does not go to 0. So therefore, f is not uniformly continuous. Okay. I'll tell you another thing, another important result, another theorem. Suppose a function is given, defined in this way. Okay. This is continuous. Okay. If f is a function like this, continuous, then f is uniformly continuous if and only if f can be extended continuously to closed interval AB. Okay. So if it is only one-sided, then I just want to extend it further. Because, of course, by the way, there is before that, I have to just give you a very important stuff. Okay. So next, before that, if f is a continuous function on a closed and bounded set, because this is closed interval, and it's a bounded set, it's a continuous function, then f is uniformly continuous. Okay, every continuous function is uniformly continuous on closed and bounded interval. That's why, I don't know whether you have observed or not, from the beginning, all my examples I'm dealing with unbounded intervals. Okay, because on closed and bounded intervals, you have uniformly continuous. Every continuous function is uniformly continuous. Okay, so I'll quickly give you an application, and then I'll go for questions. Okay. Suppose you take f of x. Okay. F is a function from open 0 to R. F of x equal to root x. Is it a uniformly continuous function? Okay. Let me ask another question. F is a mapping from open interval 0, 1 to R. F of x equal to sine 1 by x. Third, f is a function from 0 to pi by 2. F of x equal to tan x. Fourth one, f is a function from 0 to pi by 2, or doesn't matter. F of x equal to x square sine 1 by x. Okay. Now we will apply this theorem to check whether these things are uniformly continuous or not. Okay. All right. So first one. Yeah, first one here. So can you extend it to f from closed interval 0, 1, 0, 1 to R, the same function. Open interval 0, 1, to closed interval 0, 1. Can you extend it? If you extend it, what is f of 0? I can choose, since root x is continuous near 0, I can extend this by defining f of 0 is equal to 0, f of 1 is equal to root of 1. So, okay, maybe I call it as this f tilde of x equal to root x. So therefore, f is uniformly continuous. Okay, so this is gone. Oh, sorry. Okay. Now, next, what about this? Is such a function continuous? Can this be continuous at 0? No matter what value you define at 0. No matter how we define this function at x equal to 0, no matter how we set f of 0, f is discontinuous. Okay, because there is a sequence xn converging to 0 along xn equal to, let's say, 1 by 2n pi, and maybe you take yn is equal to 1 by 2n pi plus pi by 2. Okay, then f of xn along this sequence is 0 and f of yn along this sequence is 1. So therefore, you cannot make it continuous at 0. So therefore, f is not uniformly continuous. Okay. Now here, what about f of 0? Tan 0 is 0, right? Can continuously extend it at 0. But what about tan pi by 2? So you can't extend at pi by 2 because tan pi by 2, that means when x is close to pi by 2, tan x is tending to infinity. So therefore, extend it to 0 to pi by 2. So that means you can't, here also, you can't extend it to 0, 1. So therefore, f is not uniformly continuous. And then here, for the last example, f of x equal to, x square sine 1 by x. And you can actually put, if you put f of 0 is equal to 0, and f of x equal to this, then what happens? F of x equal to, x square sine 1 by x. When x is between, 0 to pi by 2, and if you put 0, when x equal to 0, okay, you define a new function like this, and then a trivial exercise for you is to check of course, at 1, how do you define? Sine 1. Sine 1 when x equal to 1. Okay. Now, what about this f bar? F bar is a function from 0 to pi by 2. 0 pi by 2 to r. So, check that this f bar is continuous. Since you can extend it to a continuous function, this f is uniformly continuous. Okay, this is a very, very powerful tool. Okay, and without stating any application, of course, applications your teachers can tell you better. I'll give you two more important results. uniform continuous functions take Cauchy sequences to Cauchy sequences, and that means image of a Cauchy sequence is again a Cauchy sequence. If xn is a Cauchy sequence, then f of xn is a Cauchy sequence. Okay, that's the nature of uniformly continuous function. Okay, so I can use this to quickly show that f is a function like this, x going to 1 by x is not uniformly continuous. Why? Because I choose xn is equal to 1 by n, which is a Cauchy sequence, but f of xn, what is it? F of is 1 by n, so that is equal to this sequence n is, okay, it's because xn is a Cauchy sequence, but it is not a Cauchy sequence. Okay, image of a Cauchy sequence is not a Cauchy sequence, therefore f cannot be uniformly continuous function. Okay, and the last thing, if f is an interval a b to r, okay, is differentiable and f dash is bounded, then f is uniformly continuous. Okay, this is also a very important thing. A proof, I leave it to you as an exercise. Okay, I give you hint. Hint is use the Lagrange mean value theorem. Okay, so I think with this, I stop my lecture, and your questions are welcome. Yeah, I'm ready for questions or comments. Yeah, I'm done with my lecture. I'm waiting for your questions or comments.
Excuse me, sir.
Yeah.
How does uniformly continuity contributes to the study of differential equations, sir? Your background is from differential equations, sir. Uniform continuity and differential equations.
Yeah, see, the thing is, the answer lies in the last exercise that I gave you. If a function is differentiable and f dash is bounded, then f turns out to be uniformly continuous. Okay. Suppose you know a priori that solution to differential equation by some methodology. Suppose if you can show that this has some weird oscillations, and if it is not uniformly continuous, then you can say something about the existence of the solution of the ODE. Okay. So in other words, suppose I have an ODE. Okay, in my hand, I want to look at the solution of the ODE, and a priori I can show that it oscillates infinite number of times, in a bounded interval. Then I can say that straight away, okay, for this ODE there is no solution. Okay, suppose it has two different suppose I know, yeah. This is a very important thing in the study of ODEs in the context of well-posedness. Yeah.
Good morning, sir.
Yeah.
F and G are uniformly continuous. Can you explain with an example? F into G need not meet.
So that's what I gave. Suppose you take f equal to, maybe I'll write down. Yeah. Suppose f is a function from O. Okay. G is again another function. G of x and f of x, they are same. That is equal to x. Then what is f into g? That is x square, right? So now this fg is a product of two functions, is a map from open interval 0 infinity, closed 0 infinity to r, with fg of x is equal to x square. In the example 2, I have shown at the beginning of the lecture, I have shown that this fg is not uniformly continuous. You see here or here also. F of x equal x square is not uniformly continuous. So, product of these two functions is x square, and fg is not uniformly continuous. Okay. Does it answer your question?
Okay, sir.
Yeah.
Good morning, sir.
Yeah. Good morning, Amma.
Show that every uniformly continuous function on a bounded set is also uniformly bounded. Can you explain?
No, I did not understand. What is it? What is the question?
Sir, show that every uniformly continuous function on a bounded set is also uniformly bounded.
Uniform. It is bounded. You mean bounded, not uniformly. Every uniformly continuous function is bounded. Okay, it's a let us try to prove it. Yeah. Yeah. What is the thing? Every uniformly continuous function on. Tell me what is the statement you want me to prove? Hello, Lavanya.
Lavanya,
Yeah.
please respond.
Yeah. What is the question? You.
Lavanya, ask us.
Sir,
Ah.
every uniform continuous function on a bounded set is also uniformly bounded.
That's the point I want to ask her. Okay, every uniformly continuous function on a bounded set is bounded. Okay, so f is a function from distance j to r. It's uniformly continuous. Then show that. Okay, given. Okay, and claim.
ఆయన చెప్పేటప్పుడు చెప్పాడు అప్పుడు రాసేసాను అడిగిందా
F is, F is bounded. Okay?
ఎగ్జాంపుల్ చెప్పమని చెప్పాడు
The bounded set is bounded. Okay. In fact, I'll tell you something stronger result than what you told me. In fact, I can give you a growth rate, bound for the growth rate. So this mod f of x is less than or equal to a plus b into mod x. Okay. If f is uniformly continuous function, no matter whether it is on a bounded set or unbounded set, you don't care. There exists two constants a and b such that f of x equal to this for every x in the domain. Okay, for every x on the domain of function. In fact, this kind of result is true. Okay, if f is uniformly continuous, then there exist two constants a and b such that mod f of x is less than or equal to a plus b into mod x. Okay, suppose if you can prove this, then whatever you have asked is a corollary to this statement. Why is it a corollary? If, on a bounded set, mod x is less than or equal to some number. Okay, so modulus of f of x is less than or equal to a plus b into, let's say, capital M. So therefore f is bounded. Okay, okay, fine. So what you should understand means what you should now take it is, if f is a uniformly continuous function, okay, then there exist two constants a and b such that this happens for every x in the domain of f. Now let's try to prove this. All that you need to do is you take epsilon equal to 1. Okay, if you take epsilon equal to 1, since f is uniformly continuous, so what happens? There exists delta such that x minus y, or maybe x minus x naught, we put, you fix a reference point. Okay, less than delta implies f of x minus f of x naught. Okay, less than 1. Okay, so you have this. So what you have is you fix x naught here. And you have this result. Now, what you do is, and this delta, since it is independent of x naught, okay, delta is independent of x naught because of uniform continuity, independent of x naught. So what I do is I put x naught plus delta by 2, okay, and then here x naught plus 2 delta by 2, 3 delta by 2, and so on. Okay, I can cover this region. Okay, now what you have, you start with f of x, okay, f of x in modulus. This is less than or equal to, okay, not less than or equal to, maybe I'll just state, I'll write one more step in between so that you understand it clearly. Okay, suppose my x is here, trapped between x naught plus n delta by 2 and x naught plus n plus 1 delta by 2, isn't it? It is actually, I keep on putting these marks, what is it, special points, identifying the special points, x naught plus 2 delta by 2, 3 delta by 2, n delta by 2, n plus 1 delta by 2, and so on. Every element in the domain should be in one of the intervals, either in the first interval or second interval or third interval, and so on. Okay, let us assume that it is in this interval. Okay, it is in n plus 1th interval. N delta by 2 is strictly less than x naught plus n plus 1 into delta by 2. Okay, so what I do is I start with this x and then I keep adding the missing points. What are the missing points? These nodes I will keep adding. What is the previous node? If I am here x, what is the previous node? Previous node is x naught plus n delta by 2. I have subtracted, so I will add x naught plus n delta by 2. And then what? And then after that, what do I do? I add and subtract the previous node. What is the previous node? N minus 1 delta by 2. So if I have subtracted, I have to add x naught plus n minus 1 delta by 2. And so on. I keep doing it till what? Till I reach this starting position, right? I keep adding and subtracting. I have to add, no, sorry. What is it I have here? Okay. This is a beautiful result actually, whatever you have asked. So f of x naught plus 2 delta by 2 minus f of x naught plus delta by 2. Okay. This is the extra thing that I'm adding, and then plus f of x naught plus delta by 2 minus f of x naught, and then the last one that's our is f of x naught. Okay. So this is all that I did was I just added these nodal points and then subtracted. I did not do anything new. Okay, just addition and subtraction. Okay. Now what I do is I just write these things as pairs. What are the pairs that I want to keep? So X, what is X here? This X and the node before it. So I join them. So when I break this modulus into pieces, what is that I have? This X plus Y, if I have modulus, this is less than or equal to mod X plus mod Y. This is the triangle inequality. By the way, this kind of adding and subtracting certain quantities and writing this number f of x as, this kind of sum, it is called the telescopic sum. Okay, you know how you open telescope? First it will be like this, simple telescope. After that, what you do is you keep stretching it, right? Then in that there will be a small thing, and then in that there will be a smaller thing. This is how you stretch a telescope, right? And if you want to fold it, you just press it. This end point will be the starting point of the another, and then this end point is starting point of another cylinder, and finally you can fold this telescope like this. You can compress. That's why this is called telescopic sum. Okay, by the way, so I use triangle inequality and I keep doing like this. I put moduluses everywhere and I get this. All right. Now, so how many such terms are there? This is, how many such terms are there? This is the first term. How many ever at, this is the first term I have, n terms are there. Okay. So each term is less than 1. So I have n plus mod of epsilon. Of course, there is nothing great about 1. I can put epsilon. Okay. So n epsilon plus f of x naught in modulus. All right. So what about f of, what is the estimate that I have proved? I have proved that f of x is less than or equal to n epsilon plus this. All right. Yeah. Now I have given you 90% of the proof. You have to fix the proof now. Now, in fact, I have given you all the ingredients. If the function is bounded, then what happens? Can it can n go to infinity? If the function is if the domain is, sorry, if the domain of f is bounded, can this n go to infinity? It cannot go, right?
Yes, sir.
It cannot go. It has to be only finitely many up to this. So that means there is a bound for n, and epsilon is fixed. So therefore this cannot grow more than certain bound. F of x is less than or equal to this bound plus f of x naught. Therefore f is bounded function. Okay. If j is bounded, then there exists capital N belongs to natural number set such that, so n into delta, yeah, so what is that thing? Yeah, x naught plus x naught is the starting point of the interval. That's what I say. Such that n delta by 2 x naught plus n delta by 2 x is less than this for every x belongs to J. Therefore, f of x in modulus is less than or equal to this capital N plus f of x. That shows that this f is a bounded function. Okay, this is a beautiful question, and the answer lies, the hint lies in telescopic sum and definition of uniform continuity, and we have not used anything fancy. Okay, you have actually divided this bounded intervals into these pieces. Each piece is having length less than delta by 2. How many such pieces are there? Only finitely many pieces are there. Okay, capital N pieces are there. That's it. Okay, so that completes the proof.
Thank you, sir. Thank you for your clear and examples. Hello.
Yeah, Chepandi.
Sir, now vote of thanks by Sri Shravani, B. Shravani.
Madam, camera on చేయండి madam.
I am honored to propose the formal vote of thanks. First of all, I thank the Commissioner of Collegiate Education for their support in organization of various programs. I express my sincere gratitude to our beloved principal, Dr.D.KALYANI, for granting us permission to organize the program. I am very much grateful to Professor T. Suman Kumar for accepting our request for being the resource person for the today webinar. And he has enlightened participants with his wonderful presentation on uniformly continuous functions. I thank Sri J. N. Suresh Kumar, JKC FTM of this college, for all the technical support he has given. Last but not least, I thank all the participants and students for making this program successful. Thank you all.
Thank you, sir. Thank you for accepting our
Yeah. Yeah, thanks.
sir. Thank you very much, sir. Thank you.
Okay, sure. Bye. Shall I log out?
Okay, sir. Yes, sir.
Thank you.